Welcome everyone, I'm Winston.
And I'm Elizabeth.
Today we're diving into something truly exciting, how biochar is transforming the concrete industry, making it not just sustainable, but climate positive. We're about to explore how this humble material could revolutionize construction, reduce emissions, and build a greener future. Part 1. First off, what exactly is biochar? This comprehensive analysis examines the multifaceted integration of biochar into concrete systems as a transformative approach to achieving substantial carbon sequestration and climate-positive impacts in the construction sector. The investigation reveals that biochar-enhanced concrete represents a convergence of advanced materials, science, environmental engineering, and climate technology, offering quantifiable pathways to reduce the construction industry's carbon footprint while enhancing material performance. Through systematic examination of production methodologies, carbon sequestration mechanisms, and integration strategies, this analysis demonstrates that biochar incorporation can achieve up to 23% reduction in global warming potential while simultaneously improving concrete durability and mechanical properties, positioning this technology as a critical component of sustainable construction practices and climate mitigation strategies.
Definition, composition, and classification. Biochar represents a sophisticated carbonaceous material produced through controlled thermochemical conversion processes. Fundamentally distinguished from conventional charcoal by its intended environmental applications and standardized production parameters. The International Biochar Initiative provides the most widely accepted definition, characterizing biochar as the solid material obtained from the thermochemical conversion of biomass in an oxygen-limited environment. This definition emphasizes the critical importance of oxygen-limited conditions, which prevent complete combustion and preserve the carbon-rich matrix that defines biochar's unique properties and applications. The composition of biochar exhibits remarkable complexity, consisting primarily of carbon and ashes, with the specific elemental composition varying significantly based on feedstock selection and production parameters. The material's fundamental structure comprises a lightweight black matrix that, despite its name, remains sterile immediately following production and only develops biological activity through subsequent exposure to biota. This characteristic distinguishes biochar from naturally occurring organic materials and highlights its potential for controlled environmental applications. The atomic ratios of biochar, particularly the hydrogen to carbon, HC, and oxygen to carbon, OC ratios, serve as critical indicators of material properties. With both ratios decreasing during the carbonization process, due to the release of functional groups containing hydrogen and oxygen. Classification systems for biochar have evolved to address the material's diverse properties and applications, with the International Biochar Initiative developing comprehensive classification tools that assess multiple physico-chemical parameters. The classification framework encompasses 4 primary property categories: carbon storage value, fertilizer value, specifically for phosphorus, potassium, sulfur, and magnesium, liming value, and particle size distribution. The carbon storage value represents a particularly critical classification parameter, quantified through the organic carbon concentration estimated to remain in soil for at least 100 years, designated as BC per 100. This classification approach enables systematic evaluation of biochar's long-term environmental benefits and supports informed decision-making for specific applications.
Detailed production, methods and processing technologies. The production of biochar relies primarily on pyrolysis technologies, which can be broadly categorized into slow pyrolysis and fast pyrolysis systems, each producing distinct biochar characteristics and co-products. Slow pyrolysis operates at lower heating rates, 0.1 degrees C to 0.0 degrees per second, with extended residence times exceeding 30 minutes. Conditions that favor biochar production over liquid and gaseous products. This approach typically yields higher biochar quantities with enhanced carbon content and structural stability, making it particularly suitable for carbon sequestration applications. The process becomes self-sustaining as pyrolysis gases are combusted to provide the necessary thermal energy, creating an efficient closed-loop system. Fast pyrolysis employs significantly higher heating rates, up to 1,000 joules per second, with residence times under 2 seconds, primarily targeting bio-oil and syngas production rather than biochar maximization. While fast pyrolysis produces smaller quantities of biochar, the resulting material often exhibits different physicochemical properties that may be advantageous for specific applications. The choice between slow and fast pyrolysis depends on the intended end use, with slow pyrolysis preferred for carbon sequestration applications and fast pyrolysis more suitable when co-product recovery is prioritized. Temperature conditions during pyrolysis exert profound influences on biochar properties, with production temperatures particularly affecting molecular carbon structure and material stability. Initial pyrolysis at temperatures between 450 degrees and 550 degrees produces biochar with amorphous carbon structures, while temperatures exceeding this range progressively convert amorphous carbon into turbostratic graphene sheets. Higher production temperatures generally increase biochar conductivity, aromaticity, and intrinsic recalcitrance, properties that correlate directly with carbon sequestration potential and environmental stability. Temperature optimization represents a critical balance between maximizing carbon retention and achieving desired material properties for specific applications. Feedstock diversity in biochar production encompasses an extensive range of biomass sources, including woody materials, agricultural residues, animal manures, and organic waste streams. Each feedstock type imparts unique characteristics to the resulting biochar, with woody biomass typically producing biochar with higher carbon content and greater stability compared to herbaceous or aquatic plant sources. The selection of appropriate feedstock requires consideration of carbon content, availability, cost, and intended application. With higher carbon content, feedstocks generally yielding biochar with superior carbon sequestration potential. Advanced production systems are increasingly incorporating artificial intelligence to optimize feedstock selection and processing parameters, enabling real-time adjustments to achieve specific biochar properties.
Fundamental physicochemical properties. The surface area and porosity of biochar represent critical properties that determine its performance in various applications, with values typically ranging from 8 to 132 m3 for surface area and 0.06% to 0.03 cm3 for total pore volume. Under optimized production conditions, biochar surface area can reach up to 490.8 m3, with total pore volume extending to 0.25 cm3, values that approach or exceed those of commercial activated carbon. The pore structure encompasses 3 distinct categories according to International Union of Pure and Applied Chemistry standards: micropores, less than 2 nm, mesopores, 2 to 50 nm, and macropores, greater than 50 nm. Micropores contribute most significantly to surface area values, while the distribution between micropore and mesopore volumes varies widely among different biochar types. The development of biochar's porous structure occurs through complex mechanisms during pyrolysis, including water loss during dehydration and the release of volatile constituents from the carbon matrix. These processes contribute to the formation of rudimentary pores that subsequently develop into the characteristic pore network that defines biochar's functional properties. The pore size distribution represents a significant parameter for characterizing structural heterogeneity, with implications for sorption capacity, water retention, and interaction with cementitious materials in concrete applications. Gas adsorption techniques provide the primary methods for analyzing biochar surface area and porosity, though additional characterization methods are required for comprehensive macropore analysis. Carbon structure and aromaticity constitute fundamental properties that determine biochar stability and environmental persistence. The aromatic molecular structures within biochar can be characterized by aromaticity indices, representing the proportion of aromatic carbons and aromatic domain sizes, indicating the number of conjugated aromatic rings within polyaromatic domains. These properties significantly influence biochar's chemical reactivity, sorption behavior, and long-term stability in environmental applications. Solid-state nuclear magnetic resonance spectroscopy provides the primary analytical method for determining aromaticity in dishes, though highly conjugated aromatic structures can present detection challenges that require specialized analytical approaches.
In part 2, we'll cover mechanisms of carbon sequestration. We hope to see you there.
Bye.